Today's daily code problem of the day is minimum time to visit a cell in a grid, number 2577. For this problem, we are given an m by n matrix called grid, consisting of non-negative integers, where grid of row of column represents the minimum time required to be able to visit the cell row column. This means that we can visit the cell row column only when the time you visit it is greater than or equal to grid of row column. So we are standing at the top left cell. We're going to start there always at the 0th second, and you must make a move to any adjacent cell, meaning up, down, left, or right. And each move takes 1 second. So we want to return the minimum time required in which you can visit the bottom right cell in our matrix. If you can't visit it, you'll return -1. So we're going to start at time is equal to 0, and we're going to start in this top left cell. Our goal is to reach this cell, the bottom right cell. So at time is equal to 0, we are in our top left cell. When we move, time is going to be equal to 1. So we can move to an adjacent cell equal to 1, which happens to be to our right. So we can move here. So now time is 1. Same thing, we can move to a cell that's either 1 or 2, and we can move to this cell, because this cell is 1. So now time is equal to 2. Oh, we can move to this cell since time is equal to 2. So boom, we move to this one. That makes time equal to 3, because we have now moved once, twice, 3 times. So time is now equal to 3. However, the only cell we can move to in time is equal to 3 is the one above. If we move to the right, time still equal to 4, so we can't go to 5. We can't go to 8 because time would be equal to 4. So what do we do here? We are able to actually traverse backwards. So we can move back 1 cell, adding 1 to our time. So now time is equal to 4. And then we can move back to 2. So time is now equal to 5, which is going to allow us to traverse to our 5 node. So now time is equal to 6. And then we can traverse down to our bottom right corner, making time equal to 7. And so 7 is what we are going to return as our answer. Let's say instead of traversing back and forth, we went up. That's going to make time equal to 4. We could go right, making time equal to 5. We could go down, making time equal to 6. And then down, making time equal to 7. So in this case, it is the same. However, by traversing back and forth, we possibly get rid of having to make bigger loops around, or getting stuck behind, let's say, an 8, which we have to then wait until time is equal to 8 before we can even go past it. In our second example, if we look down here, at time is equal to 0, we are in our top left. Our goal is to reach 4. However, we can't move anywhere. If we move to the right, time is going to be equal to 1, which is less than 2. If we move down, time is equal to 1, which is less than 3. And there's no cells that we can bounce between for us to be able to increment our time so we can move to the next cell. Because of this, we can simply return -1. So in our code, we're going to be able to implement a base case where if this cell directly to the right of our start point and this cell directly to the bottom of our start point are not equal to 1, then we can return -1, right? Because there's no way for us to escape our top left cell. So let's go ahead and jump into our algorithm and approach. The shortest path problem is very simple and means we need to use a Dijkstra algorithm. This is the same algorithm we used yesterday, so if you want to check out yesterday's video to learn this algorithm even more, go for it. But for Dijkstra's algorithm, we're going to use a priority queue. So we're going to use a priority queue to process cells based on the earliest time we can reach them. We're basically going to be treating them as weighted nodes in a graph. We'll then track our visited cells. So we'll use a visited array to avoid processing our same cell multiple times. Let's say we've already traversed 2, 3. We don't want to have to, we already know that from 3 going down here, that's the shortest length. Or going from 3 down here, that's the shortest length, so we don't want to have to reprocess it. So we're going to simulate movement. For each cell, we'll calculate when it has been accessed and determine the time required to move to neighboring cells. So if we're at 2, we're going to calculate the shortest time to reach the next cell, which is 3, shortest time to reach the next cell, which is 2, shortest, so on and so forth. But by the time that we do all of this, it's the same as moving from 2 to 5. So we might as well just go from 2 to 5 to 6. Then we are going to handle our waiting. If we arrive at a cell before it's accessible, we will wait until the cell is open, ensuring we meet its constraints. So if we're at 2 and we want to traverse to 5, we will simulate waiting by simply doing whatever our time is and calculate that into 5 minus 2 is 3. The difference is 3. Or if our time is at 4, all we need is 1. But if we're going to traverse for 1, we're going to have to traverse for 2 because we have to go back and forth, which is 2 units of time. We'll implement this in our code. So let's go ahead and jump in to set up our Dijkstra algorithm. First thing we're going to do is if both initial moves require more than 1 second, it's impossible to proceed. That's our base case. So if grid of 0 of 1 is greater than 1 and grid of 1 of 0 are both greater than 1, then we're going to have to return -1 because we cannot escape our spawn area. Next thing we're going to do is set up a couple variables to help us with our Dijkstra algorithm. We're going to have our integer rows is equal to grid.length, and then we're going to have columns is equal to grid of 0.length. Then we're possible movements. We're going to calculate our possible movements, which is up, down, left, and right. So we're going to have a 2D integer array called directions, which is equal to 1, 0, -1, 0, 0, 1, and 0, -1. Those are the 4 possible directions that we can traverse in our grid, and so we'll keep track of those to implement them later. We'll also have a Boolean 2D array called visited, which is simply going to be a map of our grid, but it's going to keep track of what cells we've already visited. So we're going to have a new Boolean of rows of calls, which will simply keep track of what cells have already been visited by our traversal. We'll then have a priority queue, which is going to store the time of each cell and then the row and column of each cell. So it's going to look like this. At cell 1, we'll do something other than just once. At cell 0, 1, 0, 1, 2. So at cell 1, comma 2, we have the value 2. So in our priority queue, it's going to be stored as 2, 1, 2. 2 being the time, 1 being the row, and then this last 2 being our column. So that's how we're going to store it in our priority queue. So let's go ahead and implement that. We're going to have our priority queue. It's going to store integer arrays, just how I just showed you. And we can call it our PQ, which is equal to a new priority queue. Now, when you're implementing a priority queue like this, you need to have a way of sorting your elements. So typically, I believe they are sorted from least to greatest. However, in our situation, we're going to want from greatest to least. So we're going to take an element A in our priority queue and an element B in our priority queue. We're going to use a lambda function, which is what this arrow is, which is simply like having a new complete function, like minimum time. However, we're only using it once, so it's going to be very small, and we're going to just implement it straight into our code. So our lambda function for this is going to be integer dot compare a of 0 and b of 0. So we are going to compare the time of array A and the time of array B, and whichever one is greater, or in this case, whichever one is, if A is less than B, then A will come before B. So it's going to sort it from least to greatest, so that way we can traverse the smallest times first. After that, we can then jump into adding things to our priority queue. So the first thing we're going to want to add to our priority queue is our initial node at time 0. So PQ is going to add a new integer array, and we are going to initialize it as whatever values at grid of 0, which hopefully is 0. And that's at position 0, 0. So that's what's going to initialize in our priority queue. Using our priority queue, so we're looking at node 0, 0. What we're going to do is we're going to look at all of its neighbors and add those to the priority queue as well. We will then look at whatever the smallest neighbor is going to be at the top of the priority queue. So let's say we're now at node 1, because that is what's at the top of the priority queue. We're going to add all of its neighbors. So we're going to look at 0. Hey, that's already been added. We don't need to do that. We'll add 1. We'll add 3. All right. And then we'll traverse the next smallest node, which is this one. We'll look up here. That's already been added. That's already been added. So now we can do 3 and 2. And then again, we'll go to the smallest next node. So then we'll look up here, look over here, look over here, look over here. We'll see that 1 has already been added, so we don't need that one. 3 is the next smallest node. So then we can continue to do the same thing. It'll see that those nodes are added. Traverse here. That's the only place it can go. Same thing again. 3's already been added, so 5 is the only place we could go. We're at 5. Traverse 6. Boom. And then it will go back. Since it found 6, it'll then go back all the way to where it was, and it will go to the next smallest node, which happens to be 3. Either one of these 3's. And it will continue to do that until it traverses through each possible path from each node, ultimately finding the smallest path. So let's go ahead and implement that code. So while not PQ dot is empty, so basically it will traverse every single possible node. We'll have an integer array called current, which is going to be PQ.pull. We're going to get whatever is at the top of our priority queue currently, and our time will be equal to current of 0. Our row will be equal to current of 1, and our column is going to be equal to our current of 2, which is what we initialized right here. We will then take this information and check if our row is equal to rows minus 1, and our call is going to be equal to calls minus 1, meaning we are at our target point, rows minus 1 and columns minus 1, which is our last cube square. We will return the total time it took. Otherwise, we will skip a cell if it's already been visited. So if visited row of column, we will continue, which skips this iteration through the loop. Next, we will have our visited of row of column, and we're going to set it equal to true, because if it hasn't already been visited, we are now currently visiting it, so we don't need to visit it in the future. And then we're going to try and traverse all 4 directions. So for each integer array d in directions, which is why we initialized that directions array earlier, this is going to allow us to traverse up, left, down, and right. We're going to have an integer called next row equal to row plus d of 0, and then our next call is going to be equal to call plus d of 1, and then we'll check if this square is not valid, we'll pass it our visited, the next row, and the next column. We will continue. So our next row is going to be row plus d of 0. So it's going to be one of these four options. So d of 0 is either going to add 1, subtract 1, add 0, or add 0. And then column is either going to add 0, add 1, or subtract 1. And then we'll call to a helper function called isValid, which is basically just going to check if that position's out of bounds. If the position is not out of bounds, we will calculate the wait time needed to move to this cell. So the wait time will mean if we are not currently at a acceptable time. Say if we're at 2, we want to traverse to 8. We're going to calculate how long do we have to wait before, or basically how many times we have to bounce between two nodes before we can traverse to 8. So our grid of next row, next column, minus our current time, modulus 2. If that is equal to 0, then we only have to return a 1. So we only have to wait for time 1. So question mark 1. Otherwise 0. So if this grid of next row next time minus our time modulus 2 is equal to 0, we only have to wait 1 second. Otherwise, we don't have to wait any seconds. Next thing we will do is then implement our next time value. So int next time is going to be equal to our math.max of grid of next row and next column plus the wait time that we need to take, or time plus 1. So if we don't have to wait at all, we're not going to count that because we always have to implement plus 1 to our time as we traverse. So that's it for the wait time. It's a little complex, a little confusing, but this is basically just simulating if the next node is too high of a value, we have to either bounce between two values or just go a different path, honestly. So after that, we can then add that value to our queue. So pq.add new integer array, and we're going to pass it the next time, next row, and the next column. And that will be traversed in the future. If for some reason we are unable to find our row is equal to rows of -1, columns equal to columns of -1, we are going to have to return -1 because we were not able to find our solution. Now let's go ahead and define our isValid helper function. So this is going to be a private. It's going to return a Boolean. It's called isValid. It's going to receive a Boolean 2D array called visited, an integer called row, and an integer called column. And all we're going to do is return if row is greater than or equal to 0 and column is greater than or equal to 0, meaning that we're not out of bounds on the upside, going up, or left. And then we're going to return if row is less than visited.length and column is less than visited of 0.length. And we're going to check one more thing, that it's not already been visited. And that's it. So we are checking to make sure we didn't go out of bounds from the top or the left, making sure we didn't go out of bounds from the right or the bottom, and then we're making sure that the node hasn't already been visited, so then we can add it to our array to be traversed, or our priority queue to be traversed. So let's go ahead and run this. This passes our test cases, and if we submit it, It passes all solutions. Thank you, and follow for more daily code solutions. Check out the links in my bio if you want to learn how to code today.